Yeah, today we talk about the Robin boundary condition, and Robin boundary condition is usually called also mixed boundary condition because so far we learned how to impose Dirichlet boundary condition and Neumann boundary conditions, and Robin boundary condition is a combination of these two boundary conditions. Then there were some questions about why energy norm is equal to u e square minus u h. So there's no e square. So we will comment a little bit about that. Then after that, we will move to polynomial spaces. In 2D. So we're going to move to 2D polynomial spaces. And if we have time, we will do finite element in 2D. We start, of course, finite element in 2D is quite big. We just start finite element 2D. So I uploaded my notes for today, so you can just download and take a look. So if you look to these Robin boundary conditions in the book, they use a little bit different notation. So I use a bit different notation. So it will be like a complementary documentation for you. So you can just compare what's the difference between my notes and the book. Of course, both of them are correct. It's just the way that they write boundary conditions a little bit differently. So example in 1D, we are still doing 1D finite elements. So let us consider the following differential equation. So here is minus epsilon u prime equals to f when x is between 0 and 1. And we have the following mixed boundary condition. So alpha u 0 minus epsilon u prime 0 equals to beta g0. And this is on the left, and on the right we have alpha u1 minus epsilon. This is plus now, epsilon u prime 0, no 1. So here is equal to beta g1. Yeah, so here we have many parameters. We have epsilon, positive, alpha, and beta. So alpha bigger than 0, beta, it's also non-negative, epsilon is positive, given constants or parameters. Okay, so you see that if we wouldn't have this part, then it would be just Neumann boundary condition because we are prescribing boundary condition for the derivative. If you wouldn't have that part, it would be Dirichlet boundary condition. So the boundary conditions are prescribed. We know exact solution on the boundary. Now what to do when it is a mixed case? So the reason that we discuss this, usually in finite element codes, by default, they assume that we have in general mixed boundary condition. So they construct all the polynomial spaces, they construct meshes, discretization, all the matrices. So matrices, in this case, it would involve all the boundary points as well. So we are not dropping anything. Then after looking, so what are these parameters, alpha and beta? So epsilon we cannot change because this is given by physics. It's an equation. We can actually decide what boundary condition should be imposed. And in the lab, we practiced at least 2 ways of imposing boundary condition for the linear system. So remember, the first row we added, like the first element we replaced to some big number. And also the second way was we moved the rows corresponding to the boundary. We replaced them by the identity vector on the 1, 0 everywhere else, and we prescribed the value of the boundary condition on the right hand side. So that we can do after constructing the linear system. We can also do it before doing that. When we know the exact solution on the boundary, we reduce our linear system. So our linear system would not include, the boundary terms. But as I said, in practice, it is recommended that you follow this mixed formulation. Of course, in exam and in the derivation, you can do the way that you like. But when you write coding, and you will see it in two-dimensional case when you have complicated geometry, for example, something like this, then these boundary nodes, in 1D, you know that the boundary node is first row and the last row of your linear system. But here, these boundary nodes, they could be completely random. They could be somewhere in between of the system. So it is quite hard. When you remove it, it's quite hard to take, to keep track of how this affect to the solution. So, and let's just continue talking about what we have. So we have several situations. For example, if you have like alpha is huge number and beta is equal to alpha. So you see like alpha is a huge number, 10 to the plus 6, for example, and beta is also 10 to the plus 6. So we will end up to the situation that we had, I think, in question problem 2 in the lab. So we divide by alpha, it's going to be u0 here, and this term with epsilon is usually quite small, and this term would be very small. Then we just have non-homogeneous, or I wrote it inhomogeneous Dirichlet boundary condition. So here we end up by having u0 is approximately g0. So this is inhomogeneous. So on the other hand, if I follow my notes, if alpha is really big, so this notation means that this number is much larger than 1, so 10 to the power plus 6, plus 7, etc. And beta is 0, then we have u0 equals to 0. So I'm just, discussing the first one. Of course, this also values to the second one as well, because these are the same alphas. Then we have homogeneous Dirichlet. So the third case, when alpha is equal to 0 and beta is equal to 1, so then we have minus epsilon u prime 0 equals to g0. This is inhomogeneous Neumann. And the last case, when alpha is non-zero, and of course beta could be any number. We have to write one more case for the homogeneous Neumann. So when alpha is 0 and beta is of course 0, then we have minus epsilon u prime 0 equals to 0. This is homogeneous Neumann. And the last one, so when alpha is not 0, you see, when alpha is not 0, it doesn't matter what is your beta. Beta could be 0, non-zero. But the point is, on the left, we have a linear combination of u and u prime. So this is a mixed boundary condition. It's mixed, or it's usually called Robin boundary condition. Okay, so that means that you can just construct your linear system for some constants alpha, beta. Your linear system would involve these all constants. Then after, when you have the linear system, you can decide what kind of alpha you want to choose, what kind of beta you want to choose, according to the boundary condition that you have. All right, so we do it the usual stuff. So we have here differential equation. Remember the steps here we had differential equation. then we write weak formulation, then we write Gagliorkin finite element approximation, then we come to the system. So this is like a step, the usual steps that we can do. So if you do that, we multiply first this differential equation by some function v, enough smooth function, because we want to integrate by parts and move one of the derivatives. At this point, we didn't decide what is this function could be. And yeah, we get the following formulation. So we get multiply by some v, and we get the following, and integrate, of course, multiply by v and integrate. So here we have integral minus epsilon prime prime v dx 0, 1. Here we have f v dx 0, 1. For some smooth enough v, so at this point we haven't decided what is this v. So yeah, we do integration by parts in this part because we want to move one of the derivatives here. So if you notice that I include this epsilon inside the brackets, why? Because this epsilon in general, it could depend on x. So if it is constant, you can of course pull it outside. But in general, of course, this epsilon, it's a function of x. So it's that's why we usually include it inside the differentiation. Right, we do integration by parts. We have the following formulation. Epsilon u prime, v prime dx, minus, so we have these boundary terms. Epsilon u prime v 0, 1 equals to f v dx 0, 1. Okay, so let me just move this one here. Just to save a little bit space. So now we open these boundary terms. Here we get 0, 1 epsilon u prime v prime dx minus u prime 1 v 1. So you should of course help me. I'm just writing for myself. I could make some technical problems. So minus u prime 0 v 0. This is the boundary condition, equals to integral 1 f v dx. Okay, so this is what we get. And recall that we had this boundary condition. From the first one, we need minus epsilon, so minus epsilon u prime 0. So that means that here we can write minus epsilon u prime 0 equals to minus alpha u 0 plus beta g0. So of course, here g0 and g1, they are given. So these are given parameters. I should also include it here. So g0, g1, they are given. And from the second one, we find this epsilon u prime 1 is equal to minus alpha u1 plus beta g1. So we take this and we have to use this. I have to put it like this. We have to use this property here, and we get the following formulation. So here we have 0, 1, epsilon u prime v prime dx minus. So here we have this one. There is minus here. With this minus, it's going to be plus alpha u1 v1. So there is plus with this minus. Minus, it's going to be minus. Then it will be beta g1 v of 1. So this is the first term. Like that. And for the second term, we have minus here. No, I mean the whole this with minus, we replace it by that. So it's going to be minus, with this minus it will be plus alpha u0 v0. And the same here, plus, and it will be minus here, minus beta g0 v0 equals to 0, 1 f v dx. Yeah, that is what we got. And now by looking to this, to the integral, so the integral should make sense. So that means that u prime should be integrable, square integrable. And there is v, so v should be also square integrable. And yeah, later in the course, we will see when we do these stability estimates, we have to show that the scheme is stable. We usually replace v by u, so u should be also square integrable. Then we can write weak formulation as follows. So weak formulation, find u from the space V, capital V. So this space is defined. V should be square integrable. So the norm of V square should be bounded. And V prime square should be integrable. And yeah, that's it. So we don't prescribe this. We don't have the Dirichlet boundary condition here. We don't prescribe the Dirichlet boundary condition. So here is mixed because we have to solve this u prime. You know, the boundary condition is not given there exactly, but we have to solve it for the second equation for the boundary. Such that, so this formulation, yeah, let me just write it a little bit differently. So on the left, we have this is unknown. That one is also unknown. But these terms are known because G1 and G0 and beta, they are known. And V is a test function. Later, we will change it to this head function. I move it to the right-hand side and write this formulation as follows. So integral 0 to 1 epsilon u prime v prime dx plus alpha u1 v1 plus alpha u0 v0 equals to integral from 0 to 1 f v dx plus beta g1 v v1. So you see, I'm moving this one here, so to the right hand side. Then I have to move that one also to the right hand side. It's going to be plus g0 v of 0. This is true for all v from this space, capital V. So this is a weak formulation. So I can just draw it like this. It's a weak formulation. Okay, so we have to construct this finite dimensional subspace of this capital V, and for that, of course, the usual step, we have to do this triangulation. So I quickly go through. We have 0, here is 1. We split by finite number of small intervals, and we numerated x0 is equal to 0. This is x1, that is xn, and somewhere here we have IE. So IE is xi minus 1, xi. Then HE, the mesh size, is xi minus 1. What else do we need? So we denote this triangulation by the union of all these intervals. That's a triangulation. Yeah, I think that's enough information. Then we can write finite element approximation. So GFEM. Find UH from VH such that it is defined as V. So V is a continuous function in this interval 0 and 1, and restriction of V with any elements I is a polynomial degree of degree 1. So I equal to 1 to n. So this is our finite element space, and yeah, it is continuous, and it's linear, piecewise linear, continuous piecewise linear function. The dimension of this, we know that is finite, and of course the dimensions are constructed by this type of head functions. So it is phi I. Of course, here we include this on the boundary. We also have this half head functions, so phi n. And yeah, the dimension is the number of these basis functions. It's going to be, in this case, n plus 1. Such that this formulation holds. So I can just copy this. And I copy that. And we add h here. H. Okay, so this one is Kalergin finite element approximation. All right, so so far there's no news. The next step, the only thing that we can see here, there is a boundary term, it counts. So there's no, this is not integral, it's just one number, which is on the boundary. And it's also a boundary, the first boundary, that's the last boundary. But it says that we don't know solution at the boundary, because this is a contribution from the Neumann boundary condition. But on the right, these are values that are known, and they are also one value. They don't participate in this integral. And in a few minutes, we will see that these contributions will be affected only to the first and last boundaries. Let's see what is. So we have that since U is from VH, then we say that there's a sequence of coefficients from 0 to n such that UH is written or can be written as a linear combination of these basis functions that we defined a bit earlier. So it is basis functions on this picture. You can just write it as a linear combination. So the next step is we insert that to the weak formulation, now to the finite element formulation, and we also replace V with phi I. So we replace V with phi I, and we get the following system of equations. So the first one, I put the sum j equals to 0 to n. I rearrange it, and I get the following. So this is, and there is epsilon. Here is from 0 to 1, phi j prime, phi I prime. And I see that in my notes that I uploaded, I I dropped epsilon, and epsilon is missing. So I'm gonna fix it a bit later and upload it. Okay, then we have the x. The second term is plus alpha. So I'll put again the sum because I'm replacing UH by the sum. First, I will just put the sum, then we will simplify, because remember these head functions, they don't have a common support with many each other. So if you multiply, for example, this head function by that one, the product is 0. So that's why I write first with the sum, then after simplification, we just get some numbers. So here we have epsilon, no, alpha, j equals to 0 to n, psi j, and here we have phi j 1, so it is at 0.1, phi I 0.1, plus the same term but with 0.0, so j equals to 0 to n, psi j, phi j at 0.0, phi I at 0.0. This one is equal to integral from 0 to 1 f phi I dx. So I'm writing this part plus beta g1 phi I1 plus beta g0 phi I0. So instead of v, we put phi I. And this formulation is true for all I from 0 to n. So we have n plus 1 equations and n plus 1 unknowns. These are unknowns, the size. All right. So next step, if we look to this product, I mean, this product, you take j equals to 1, for example. When j is equal to 1, then it is phi 0, 1 times phi 0, 1. So if you look to this figure, of course, this phi 0 is non-zero in this first interval, but it is 0 everywhere else. So that means that wherever you put at this point, so this phi 0, 1 is 0. With the same way, phi, so here we have phi 1. I want to say that at this point, phi 0, 1 is 0, phi 1, 1 is 0, etc. So everything is 0 except the last one. So that means that in this summation, you can choose whatever you want, but the only one non-zero element is the last one. So we write the sum j equals to 0 to n psi j integral 0 to 1 epsilon phi I dx plus alpha psi n phi n 1 phi n 1. So here I put I because we are not there is a summation. I change j's, and but i's is the same. So we cannot change I. I's are corresponding to each equation. So here we have alpha psi 0 phi 0 0 phi I 0. Everything is equal to the right hand side. So I'll just copy the right hand side here. Yeah, that's the right hand side. Okay, so we got a linear system. So I can write to move a little bit here. So I just want to have some space for notation. So the first one is A times psi. So this is the usual stiffness matrix times unknown vector that we have. The second one if you follow the notation in the book, so they call it arc-psi, some matrix R, and the right-hand side is vector B. So yeah, if you write what are the elements, because the elements of this R, everything is 0 except the first element and the last element. So that it's also n by n plus 1 by n plus 1 system. Everything is 0 except R11 and RNN. So let me just write it. Just a quick reminder, what is A? A is this type of integrals. Epsilon phi 0 dx 01 epsilon phi n prime phi 0 dx, etc. So it's epsilon, the last one, phi n prime phi 0 prime dx, epsilon phi n prime dx. The usual matrix. Let me move a little bit just to make a bit space. So then our R would be, if you look to this formulation, in phi, we have to look to this one because the first row is n. So phi 0 and phi 0 is non-zero. So that they are 1. And here we have like alpha. Here we have alpha, 0, everything is 0. 0, and the last one is alpha as well. So everything is 0 except these two rows. The first one is the first element is non-zero. The last one is the last element is non-zero. And the right-hand side is similar because here we see that phi I1, it doesn't leave except the last one. The last head function at this point is non-zero. The rest is 0. And the same here, phi 0, 0 is 1, but the rest of phi's, they are zeros. So here we have a similar situation. Let me just write it down. Do like this. So the first one is 0 to 1, f phi 0 dx plus beta g0. The second row is 0 to 1, f phi 1 dx plus 0. So everything is 0. Let me write the one from the previous, the last one. So this fn minus 1 dx plus 0. And the last one, 0 to 1, f phi n dx plus beta g1. Oh, this is the right hand side. Okay, so these elements, they are contribution of the boundary conditions. So here we have also that. Okay. There is one question in the chat. Let's see. Will the A matrix be singular? No, it will not be singular. It will be actually positive definite. This matrix A is positive definite. Do you remember what was the definition of positive definiteness? I mean, I have to recall my memory as well. Matrix A is positive definite if for any at non-zero, so non-zero vector, at transpose A eta is a number, is strictly bigger than 0. So one can prove that actually A is positive definite. So let us take this eta. I mean, eta is, they are coefficients, right? It's just a coefficient. For example, in this situation, psi is also a vector of coefficients. So if eta is non-zero, we can use eta to construct some function w such that it's a linear combination j equals to 0 to n at j phi j. W is element from this VH. Okay, so these are coefficients. Of course, we can use these coefficients and construct a linear combination. When at non-zero, that means that W is also non-zero. It's a function. All right, so let us take a look to this. What is this? It's a vector. So this transpose, that means that, let me just write schematically what is it. So this is like that vector. It's a column vector. Then n transpose, no, eta transpose A eta, this is actually row vector, because the transpose of the column vector is a row vector, times a square matrix times a column vector. It's just one number. And let me call it A. Is one number. So you multiply this row to the matrix, you will get a row. Here it's going to be row vector. So you multiply row vector to the column vector. It's just a scalar product of these two vectors. So in other words, if you write this, it's going to be the following formulation. This double summation J, of course, I equal to 0 to n. And here we have J equals to 0 to n at I, Aij, at J. So the elements of this matrix, of course, we call it Aij. And this vector notation is exactly this sum. It's double sum. So we can work out a little bit. We write what is Aij. So here we have sum of I equal to 0 to n, sum of j equal to 0 to n. Here we have n eta I. And Iij is integral from 0 to 1 epsilon phi j prime phi I prime dx and at the j. So we write, so what is Aij? Aij is the elements, they are integrals of this product. So the next step we do, we move this sum in front of this phi I, and we move the second sum in front of phi j. Of course, when we move the first sum, we have to move these coefficients as well. So we write the following. So it is equals to, we write first integral 0 to 1 epsilon, the first sum. So epsilon I equals to 0 to n eta I phi I prime. Okay, so it depends on x. The second sum is sum j equals to 0 to n eta j phi j prime of x. Everything is dx. All right, now you see that it's a sum of the derivatives, right? Sum of the derivatives. Of course, we know from calculus that x plus y prime is equal to x prime plus y prime. So we can just write the sum of the derivatives is a derivative of the sum, so it doesn't change. Therefore, we can move this derivative outside of the sum. So we can just move it like this. And we can also move that one here. All right. So what do we get? We know that this linear combination is our W. So the other linear combination is also W. And we get the following equality. So integral 0 to 1 epsilon W prime dx. And this is actually energy norm of this W. And it is non-zero if W is non-zero. And it is actually positive because norm is positive. Okay, so we prove that for any non-zero coefficients, this product is strictly positive. So that gives that A is positive definite. So the theory in linear algebra says that if A is positive definite, it's non-singular. So this is related to your question that if A is singular, A is non-singular. Actually, A is positive definite. You can always invert. Is there any question? Okay. So if there's no question, I can make one remark. So when you are doing coding, when you write finite element library, so you're writing in 1D, soon you will write something on 2D. So it is better you keep all the boundary terms. For example, here, if we would have 0 on the boundary, we usually in our formulation, when we write with pen and paper, we drop these two head functions, right? When we drop the boundary, the boundary terms are, they are not taken into account. Your linear system becomes a bit smaller. So we say that, of course, in 1D, you have only two boundary terms. But in 2D, this is not clear because you have as many boundaries as you have it on the boundary. On the boundary nodes, there could be many nodes. So it is quite difficult to keep track of them because once you drop it, your linear system becomes smaller, and because the numbering is unstructured. Finite element is unstructured meshes. So in practice, when you do when you write the program, it's easier to include all the boundary terms. You assume that you have Robin boundary condition or mixed boundary condition, for example, here. Then after implementing, calculating, and constructing your matrix, if you have a Dirichlet boundary condition, you can just replace the rows by 1 and put Dirichlet boundary condition on the right. But if you don't have Dirichlet boundary condition, it's going to be just Neumann, and the boundary contribution counts like a contribution to the right-hand side, as we have it here, as we have on this part. Okay, so I don't have anything to say right now. If you have any question, please go ahead and ask. No, so let's take a break then, 15 minutes. After the break, we quickly go through this identity. We don't spend much time. Then we will go to polynomials in 2D. All right? See you in 15 minutes. All right, shall we continue? Can you hear me?
Yes.
All right, thank you. Okay, so actually this. All right, so before the break, let me continue this recording. Okay, so before the break, what we did, we discussed how to impose mixed boundary condition, or it's called Robin boundary condition. So now we quickly go through this identity, then we will move to polynomial spaces in 2D. So for simplicity, that we assume that our differential equation is u double prime is equal to f in 0, 1, u0 equals to u1 equal to 0. So that just, I want to make the same problem as in the labs. So we write the weak formulation here. That is, find u from space V0, and the space we find it as V is square integrable, V prime is square integrable, V0, V1 is equal to 0, such that we have this integral u prime v prime dx equals to f v dx 0 to 1, 0 to 1 for all v this v0. So let us assume that we use the same triangulation that we defined a bit earlier. Then we write Gagliarkin finite element approximation, which reads find UH from V0H. So it's those elements that V is continuous in this interval 0 and 1. Restriction of V on every element is polynomial of degree 1, I equals to 1 to n, V0, V1 is equal to 0, such that the same formulation holds for this finite dimensional space. Dx equals to f v dx for all v from vh0. So what we do, the next step, usually we subtract Gagliarkin finite element approximation from the weak formulation in this small subspace, and we say that the right hand side, they are equal, they cancel out, and on the left hand side we have the error, relation of the error with the test function. Here we call it Gagliarkin orthogonality. It's 0 to 1 u minus u h prime v prime dx is 0 for all v from this vh0. Okay, so and in addition we say that the energy norm is defined by this bilinear form. So the energy norm W is AW, which is integral W prime dx 0 to 1, or it's a L2 norm of W prime there, something like this. And the identity that we wanted to prove is E square energy norm is equal to U square energy norm minus UH square energy norm. Okay, so of course, how it is obtained here, you start with the energy norm, you do some addition, subtraction, etc. You simplify, you end up to that point. But I'll do a little bit different. I say that I want to prove this identity. Then the identity is true if the left-hand side is equal to the right-hand side. So then you will see what is added and subtracted. If you want to redrive your equality, you can do it a bit later by yourself. So I want to prove that this identity, if it is correct or not. So this is, I want to check. So we put what is E. This was our E, our error. On the left, we have U minus UH E square. And on the right, we have U minus UH square E. Then we write the definition of the energy norm. It's here by linear form. And we write this as integral. So integral 0 to 1 U minus UH prime U minus UH prime dx equals to integral 0 to 1 U prime dx minus 0 to 1 UH prime dx. Okay, so the next step is we open this bracket, this multiplication of these two, expressions. We write it. We split the integrals by several small integrals. The first one, 0 to 1, u prime. Of course, this object times to that object. And there's a derivative as well, tx minus. So the second one is u times uh, and there is also u times uh. The sign is negative, negative 2 u prime dx. 0 to 1. And the last one is minus times minus it's going to be plus integral prime dx. 0 to 1. And still on the right hand side, we have 0 to 1 u prime dx minus prime dx. Okay, now if you just compare the left-hand side and the right-hand side, you see that the first integral, they cancel out. They have the same sign on the equality. Then we move the this second integral on the right-hand side. We move it on the to the left, and we show that the resulting sum of the integrals is equal to 0. So if we move to the left, there is the same integral here, but the sign is positive. Here is positive, negative. After moving, it will be positive. So it's going to be minus 2 integral 0 to 1 u prime prime dx plus 2 integral 0 to 1 prime prime dx, and if it is equal to 0. So yeah, we can divide it by 2, just we cancel it. And we can write this integral as one integral. So here you see there is prime, there is prime. We factor it out, we pull out from the brackets. So inside the brackets, it's going to be u prime minus prime. So this integral, I can write it as 0 to 1. It's actually minus prime times prime dx. If it is equal to 0, this is what we want to show, right? But here you see that this is nothing else than Gagliarkin orthogonality. So here we have integral from 0 to 1. I can just multiply by minus. So I want to make the same as Gagliarkin orthogonality. I pull out this derivative outside. So u minus prime dx equal to 0. And quickly you see that this is your error, but UH is one element from this space VH0. So that means that this is actually Gagliarkin orthogonality. So Gagliarkin orthogonality says that this object is equal to 0. So we get 0 equals to 0. So that gives that you go back all the way to the beginning, this equality is correct. Yeah. So there is one thing that I have to mention in finite element approximation. It's not correct if you use this built-in norm function in MATLAB. I will explain you in a few words. So there is a like L2 of some vector V. This is little L2. It's the one in MATLAB is norm. This vector V in MATLAB, I think it is written like that. It's 2 norm, like a 2 norm in MATLAB. So if you want to calculate the error in the 2 norm, so what does it do? Your error, so I can just draw this from 0 to 1. We split it by a finite number of. So the error is calculated pointwise. So here is pointwise. These are pointwise. E0 equals to U0 minus UH0, for example. The error is calculated pointwise, but in finite element, we have to calculate this error. So capital L2, 0 to 1. This error is different. It's an integral. So I can just draw it quickly like that. So we know that finite element approximation, it's a function. It's not a discrete point. So this was 0 to 1. For example, if your original function is like this one is your U continuous function. Finite element approximation, it finds some kind of base approximation, which is piecewise like linear function like this. So it could be somewhere here. This could be somewhere there. So it's going to be something like this function. Okay. So now if you use 2 norm in MATLAB, it constructs these points. So this is it's a distance. I'll draw it with different. So 2 norm in MATLAB is just this little distance. The little distance between this is U xi and this one is U h xi. It's a little distance for every point, but this is not correct in finite element. Our approximation is function. So we have to actually calculate. This one is our error. This is not the pointwise error. It's like a big neighborhood. Like that. So you have to calculate the integral. So you have to calculate EL2 1. So I put square here. It's the integral of U minus UH square dx. Yeah, so I think in the project, one way of calculating the energy norm is described. It's I think the error in the energy norm square is we take the coefficients of this error. We take a transpose times the stiffness matrix. We multiply it by the by its function itself. So this is our vector, you know, because if you just write it down, what do you get? It's like you know, reverse engineering the proof that we showed a bit earlier about positive definiteness. It's going to be integral from 0 to 1. It's I equal to 0 to n. Here we have ei phi I. Okay, so this is we have a derivative of that. Now j equal to 0 to n ej phi j, derivative dx. So it's like it's an integral e prime dx. So it is quite good approximation of this integral actually. So you have to calculate something like that. Yeah. So what I wanted to emphasize, this norm is not the same as L2 norm in MATLAB. So don't use L2 norm in MATLAB. Our approximation, they are functions, they are continuous functions. They are functions like this. In finite difference, your approximations are discrete points. So you know only approximation at some discrete point. You don't know anything in between. So in finite difference, usually they use the little L2 because they want to estimate how good is this approximation in that point. But this is not the case here in finite element. This is continuous function. We want to see how good we are approximating in between. All right. Do you have any questions? No questions. So let me just come back quickly. What we did, we do it like this. All right. So before the break, we discussed these Robin or mixed boundary conditions. Now we went through this identity because I got many questions by email. It's good how the Gagliorchan orthogonality is used to prove this identity. I think we went through now. And let's continue what is the next here. We did finite element in 1D. We know how to construct polynomial spaces. And we want to discuss how to do it in 2D. Then after that, we will move to time-dependent problems. So polynomial spaces in 2D. I've uploaded my course, my notes. So in 2D, the good thing with finite element, of course, in 1D, it's not so interesting. In 1D, finite element can be just equivalent to finite differences for some particular cases. Or in 1D, you cannot see so much advantage of finite elements. But in 2D and 3D, the advantage will come up because in 2D, finite element can be extended to solve any problems in these kind of complicated geometries. So we take this omega, it's some subspace of R2, and so this one is omega. And the boundary of omega we denoted by d omega. So d omega is boundary. The boundary of omega. So how to construct these polynomial spaces? We have to do this triangulation in 2D. In 1D, we know how to do triangulation. In 1D, we just take the interval and we split it by a finite number of subintervals. That's fine. how to do that in 2D. So in 2D, there are many ways, of course. In 2D, the easiest way is dividing this omega to simplexes. So omega is approximated by simplexes. So what are simplexes? I think I recently saw some good documentation in Wikipedia. I usually don't read Wikipedias, but they wrote something very good about simplexes. The simplexes are a collection of triangulars, edges, and points. So, for example, we split the domain by a finite number of these kind of triangulars. These triangulars are called simplexes. So the good thing is, they don't have to be. Of course, you see on the boundary, there's a little bit curved here. It's totally okay, but these are curved boundary. Of course, you can allow that. So if you take one of these triangulars, K, I denoted Ki. So this triangular, we say that omega is approximated by sum of I. How do I denote it? I from 0 to some, maybe M. It's a number of elements. M is number of elements. Ki. So Ki is usually called, it is element. It's also called cell. In this case, it's called triangle, etc. So this is like there's many names. The name of finite element actually counts that the number of elements that we put in this triangulation is finite. So we need to identify this triangular. We need to have 3 vertices of that. So the vertices are denoted by, let me call this Nj, for example. And Nj's, J is from 1 to, let's say, N. I call N as a number of vertices, or sometimes called nodes. Let me just call it here vertices. So a number of vertices. And we need to identify the edges as well. So for example, this edge is usually called epsilon. It's capital epsilon. And let me, I will call it with E, capital EK. And the collection of all the edges, so there are many edges there, right? Why do we need these edges? Because you see, like the boundaries, there are some kind of edges. So the collection of all edges, we call it with capital epsilon. So it's a collection of all edges. So this is like all edges. And the collection of all cells, so we usually denote it like that. It's called this TH. It's a mesh. Something like this. And of course, you have to, handle these curved geometries. But in practice, as a starting point, usually we approximate the boundary by some polygon, something like this. So the boundaries are approximated by polygons. Oh, there is one triangle here. And now if I remove this, yeah. So the boundary is approximated by polygons. You take more triangulars, you approximate it closer and closer. But of course, curved boundaries are also defined, and you have to take care of it in a separate way. And usually we say that for every element k, we define a mesh size hi, and it's a mesh size. So mesh, how do you denote it? So mesh size. So it's a mesh size. And of course, now you see that the mesh size, like in 1D, you used to take just the size of the interval, right? So the length of the interval, it was one mesh size. But this is the issue here in 2D. There's no precise definition of the mesh size. So what is a mesh size? That these triangulars, it could be like, look at this one. So what's a mesh size associated to this triangle? So there are many definitions of mesh sizes, but one of the commonly used, they take this mesh size to be a diameter of Ki. So diameter means that you take a triangular like this, and you pass some circle around it. So I have to pass the circle that it passes through all vertices, so all these vertices. Then the mesh size is a diameter of this circle. So this is like a diameter. Now this is one way of defining the mesh size. But there are many ways, of course. If you look to this stretch element here, the diameter of this could be quite big. But if you look to this little one, the diameter is, of course, is something else. And as I say, there are many ways of defining the mesh sizes. Okay, so our aim is to construct continuous polynomials, which restriction for each case, there are some kind of polynomial of degree 1, 2, 3, etc. So our aim is to construct the following. To construct this polynomial VH such that these are those V's. V are continuous functions inside this omega, but restriction of V with element Ki is a polynomial of degree Q on Ki for all I from, what did we do this numeration? From 0 to M. Like that. Okay, so if polynomial of degree Q, sometimes we just put these spaces piecewise polynomials of degree, continuous piecewise polynomials of degree Q, so something like this. Okay, so if we define that, we know that K's are finite. We have M plus 1 K's. So that gives that the dimension of VHQ will be finite. And this is something that we are looking for. And the question now is how to construct these polynomials. So these are the questions in this point, how to construct this polynomial space. So if you take one triangular, for example, here, how to construct this space of piecewise linear. So it is linear polynomials on K. So you take one triangular, we learn how to construct these polynomials. Then we take the second triangular, we learn how to construct that. You see, like when we machinery learn how to construct them, then we can construct a basis function which lives in all space. Then linear combination of the basis function would give this polynomial space that we are looking for. So if you want to define any polynomials in this triangular, we need to define, so like what was the argument that we had in 1D? So in 1D, if you have like interval like that, and if you have some function, linear functions, we say that any linear functions can be identified by 2 points, right? So you give 2 points, there is only one linear function which passes through these 2 points. So it's one of the axioms. So in 2D, any linear function, so linear function would be like a surface. So any linear functions as a surface, any linear surface which passes, inside this K, it is identified by 3 points. So we can actually use these points like x1, I put 1 point. So this is the first point. That's why I put 1. Then here x1, x2, the second point. And here we have x1, x2, the third point. And of course, we can say that any element from this P1K, for any element, they exist 3 coefficients, C0, C1, C2, such that Vx, so it's a surface, equation of surface, is equal to C0 times 1 plus C1 times x plus x1, C2 times x2. So it's like, of course, here we have a coordinate system. So here we have, let me just move a little bit, just to make some space. So we have a coordinate. This is x1, x2, and we have 3 points in this coordinate system. And we want to construct the polynomial which passes through these 3 points. Of course, you write any equation, so it's in 2D, any surface. Not any surface, but it's a plane, it's just particular case. It's like a linear combination. So that actually gives that this polynomial of degree 1 on K can be written as a linear combination of these 3 basis functions, 1, x1, and x2. Because this is actually linear combination. For any plane, you find its own coefficient, so it's just a linear combination. So that gives that this set is one of the basis sets for P1K. It's a polynomial of degree 1. If you have these 3 functions, they are just the 3 elementary functions. You can construct any element on that space. But remember, we want to extend it to the whole domain. So this omega is a combination of all these triangulars. So we want to make sure that later it's going to be our matrices will be constructed by some basis functions, like you multiply basis function to each other. So for example, remember this stiffness matrix was A integral phi j prime phi I prime Ex. So 0 to 1, like in 1D. And this phi I, phi j, this could be one of these basis functions in this case. But the problem is we want to construct those basis functions that this integral is 0 in many points. So the supports are not talking to each other. But if you construct the basis function to be like that, that will not be the case. The linear system that you will get later in the approximation, it's going to be full. So full linear systems, we don't want to solve it. Like in scientific computing 3 course, we saw that if the matrix is full, you can use any method, iterative methods, direct methods. It's going to be super expensive, and it's not. This is something that we have to avoid. So we have to find some other basis functions. So find or construct other basis functions. Basis sets. It's better to write it like that. So of course you can say that yeah, we can just use the same idea that we use in 1D. We construct these Lagrange basis functions. So Lagrange basis functions you can just extend it in 2D. The definition says that these are lambda lambda just I, so x1 j x2 j such that it is 1 if I equals to j, 0 I is not equal to j. So it's like I can just draw for example for this triangular, for that if it is 1 and 2 3, so we can construct lambda to be like this function, which is 1 here is 1, but 0 otherwise, like this. It's like how do you, is it pyramid? It's called pyramid, like tetrahedron. So if you want, this was lambda 1, so associated to node 1. And if you do the same for lambda 3, for example, here, I need to make a bit space. So here again, this is equal to 1 somewhere there, and then 0 here, 0 there. So this is lambda 2. Oh, lambda 3. So this is lambda 3. And lambda 2 would be, we have somewhere 1. So here, and 0 in other points. So this is lambda 2. So if you just take like a triangular, it's like you are constructing tetrahedrons on the every node. So yeah, one can show that you can take these basis functions. I don't want to repeat, but it will be exactly the same arguments that we had in 1D. So we can write that P1 of K can be written as a linear combination of all these basis functions, lambda 1, lambda 2, lambda 3. And the good thing with this basis function is that you see like it is 1 in one point, 0 otherwise. So we can actually extend it for all this domain. So in the domain, we had something like this. So we construct a basis, Lagrange basis function for each node so that it is 1 in this node, and we just extend the same definition, and we put 0 everywhere else inside this domain. So inside this, it's usually called patch. So a mesh containing this node. So in this particular case, the dimension of P1K would be 3. because we have three linear independent functions. Yeah, so I want to extend it. So like in this point, so it is 1 and 0 otherwise. And let us just take some patch. So I just throw it like this. When you triangulate, you get some kind of like patch, a mesh containing this node, for example, Ni, something like this. So for this, of course, this mesh, continues like that to the whole domain like this. Could be like that. And using the same definition, we construct a basis function to be 1 here, like this, and 0 otherwise. So okay, so this is phi I of x. So since x is two-dimensional, I put x bar, and it's defined that phi I of x is equal to 1 when we have this I is equal to j. There's this node, I will call it xj. Maybe I can call this node as xj, like this. Then 0 otherwise. So it's like, think about, you have your table and you put some fabric and you put a lot of nails. So you put with a hammer. So you release one nail in one time and you pull this fabric up to distance 1. So if you put up to distance 1, it's going to be like a head, right? It's like a tent, which is 1 in this point, and otherwise everywhere else is 0. It's defined in the whole domain. So in practice, this function is also called like a head functions. It's also called the tent functions. And that means that one can choose these functions. Remember, we have to construct some basis to this space. This is a space that we are looking for. Then we can take a linear combination of these basis functions, phi j's. So j is equal to 0 to n. It's number of points that you have in the mesh. And yeah, that's a basis. One of the bases of this space VH. And with this way, when you construct it in these head functions or tent functions, the dimension of this VH is going to be n plus 1. Okay, so yeah, I think we are out of time. But the idea is we work with these spaces, and all these finite element approximation that we look, they will be inside these spaces. So they are continuous. This is like we denoted here. They are continuous, and they are piecewise linear, or polynomial of degree q, of course, in this case. So it's like your solution in 2D is going to be like kind of surface, right? So you are approximating this surface by some kind of like a linear combination of, for example, this paper. It's also one element of that VH. So you are constructing by a linear combination so that this surface that you construct, they glue, you have to glue each other. So they are continuous. There is no discontinuity. But inside each triangular, there will be some, plane. So it's simple plane for q equals to 1. All right. So I think I stop here. If you have any question, I would be happy to answer. Okay, so yeah, I'm glad that we just repeated. I think we did it before in Scientific Computing 3 course. Here we just, oh, there are some questions. Will the first part of the project be graded? Yes, it will be graded, but I will grade everything at the end. So first time, I will see that you implement everything is correctly and you upload your solution. You don't have to write a long report. So it should be something that's readable and it should be correct. Then, yeah, of course, it will be graded and it will be graded as a part of big report that you will write in the end. Or is it only the last submission? No, every part will be graded. So you have 3 parts. Part A, it's adaptive finite element. Part B is finite element in 2D, you write it in MATLAB. Part 3, finite element for systems, you use Phoenix. Everything will be graded part of that. Is it the only last? No, what is? Anything is wrong in the first submission, we have chance to redo it before. Yes, of course. That's the main idea, but you have to follow strictly deadlines. I'm quite, strict with this kind of stuff. It's okay that you can submit it next year, but you will not get high grades. If for high grades, you have to follow the deadline. You have to follow writing a nice report. But if you miss something, of course, that's why we put these submissions now. You have a chance to improve it, and we will see your final report. Okay.